Welcome back to the induction motor drive class. In this class, we'll be discussing about braking of induction motor. For the braking of induction motor, we have three different methods. One is called regenerative braking, next plugging or reverse voltage braking, and the third method is dynamic braking or rheostatic braking. Dynamic braking can further be classified as AC dynamic braking, self-excited braking, DC dynamic braking, and zero sequence braking. Now let's discuss about regenerative braking. When I say regenerative braking, that indicates during braking, the power which is already available in the motor is converted and the motor now works in generator mode so that the power is fed back to the supply. So during regenerative braking, the motor induction machine works in the generator mode and the power which is already available in the motor will be fed back to the supply, which gives an effective braking. This is the motor's power equation, which is 3 into V into Is cos phi s. So V is the voltage, Is is the stator current. So stator voltage, stator current, and phi s is the angle between stator voltage, phase voltage, right? V is stator phase voltage and Is is stator phase current. So phi s is angle between stator phase voltage and stator phase current. Now, if phi s is less than 90 degree, cos phi s is positive. So I can say the power will be positive. If phi s is more than 90 degree, then I can obtain cos phi s, which will be negative. So the power will obtain as negative power. Negative power indicates it is generating mode. So power is fed back to the supply. Now, how can we obtain this regenerative braking? So this is the basic theory by which we can obtain the motor operating as a generating mode. So to obtain that, what we need to do? We need to run the motor at a speed which is more than the synchronous speed. If we can run the motor at a speed more than the synchronous speed, so omega m is greater than omega ms. If we can make this, that speed of the motor is greater than the synchronous speed, then we can say that the relative speed between the rotor conductor and the air gap rotating field, this will reverse. Rotor speed is greater than synchronous speed. So relative speed between the rotor conductor and air gap rotating field will be reversed. So if this reverses, then the rotor's induced EMF will be reversed. So rotor induced EMF is reversed. So rotor current also will reverse, and component of stator current, which balances the rotor ampere turn, will be reversed. So this, if I consider that this indicates the voltage and this is stator phase current. So this is stator phase voltage, this is stator phase current. What happens? That stator phase current is now reversed. So if stator phase current is reversed, earlier the angle was phi s, which was this voltage, and this is the current. Voltage and current, the angle is phi s. Now, due to the speed which is more than the synchronous speed, the current has reversed. So this is Is, now this is Is. So if this angle is less than 90 degree, this angle is of course more than 90 degree. So when the angle is more than 90 degree, then I will get the power which will be negative. So that will give us operation in generator mode. So how do we obtain this? To obtain this, the basic requirement is that we have to run the motor at a speed higher than synchronous speed. Now, how do we obtain that? To obtain that, one thing is, if we have the supply frequency constant, then we need to run, of course, at a speed which is more than that speed, more than the synchronous speed, which was earlier synchronous speed. If we have a variable speed, variable frequency supply available, then we can obtain a speed more than synchronous speed even at a lesser speed. Because if we reduce the frequency, then synchronous speed will reduce. Motor speed remains omega m, but the synchronous speed reduces. So finally, this will give us regenerative braking operation. Main advantage of this regenerative braking is that generated power is usefully employed instead of wasting in resistors. So it is usefully employed, but the main drawback is if we have a constant frequency supply, then below synchronous speed, we cannot employ it because the motor has to run above synchronous speed to obtain this regenerative braking. So this is the speed torque characteristics. This is the motoring operation speed torque characteristics, which we have seen before. Now it is run at a speed higher than synchronous speed and power is negative. So speed remains in the same direction. Direction of speed does not change, but the torque direction changes. So we get it in second quadrant. So torque is negative. In regenerative braking mode, this is the speed torque characteristic curve. Coming to the next one, plugging or reverse voltage braking. When I say reverse voltage braking, the phase sequence of the supply is changed. So when phase sequence of the supply of a motor running at a speed is reversed by interchanging connections of any two phases of stator, then what do we get? It's like phase sequence is changed. In that case, we'll get this plugging. But how? Because the phase sequence is changed, so we will get the rotating magnetic field which will be rotating in reverse direction. Rotating magnetic field is having the same speed, but it is rotating in reverse direction because the phase sequence has changed. So in that case, if the slip for plugging, if I take it as Sn, so synchronous speed has reversed. So I will get Sn value, which is minus omega ms minus omega m by minus omega ms. Because the direction is changed. Earlier we had omega ms minus omega m by omega ms, which is slip. Now in place of omega ms, I have to write minus omega ms. And this also minus omega ms. This theory is exactly same as when we have discussed about the induction motor's behavior if it is supplied from an unbalanced source. If unbalanced source is present, then unbalanced source is connected to an induction motor, so we'll get a positive sequence component, we'll get a negative sequence component. This is exactly the same theory. So negative sequence components, slip calculation, which we have seen it before. So now, because the phase sequence is changed, so it is in the opposite direction. Phase sequence is in the opposite direction. So the rotating magnetic field that we obtain will be in the opposite direction. So if rotating magnetic field is in the opposite direction, that indicates the speed of the rotating magnetic field, which is nothing but synchronous speed, will be minus omega ms in place of omega ms. So slip can be calculated as minus omega ms minus omega m divided by minus omega ms. Now if we simplify, we'll get it as 2 minus s. So this is the slip of the induction motor during plugging. So slip value changes. Slip value is now 2 minus s. Now with this, if I obtain the speed torque characteristics, this is the speed torque characteristics under motoring operation, this in the first quadrant. Now I want to obtain it in plugging. So what we will do, the speed torque characteristic goes to second quadrant. Suppose at this instant we are shifting it. So we are changing the phase sequence. So what will happen from here, it will come here and then it will follow this or this. Now, what is these two curves? When we consider this plugging, it's basically this graph is what we are getting. this curve 1. We get this curve. Now, if we have external resistance connected, then we get this second curve, right? In case of wound rotor motor, we can connect an external resistance. Now, when we connect an external resistance, then the braking current can be limited, and then we will get this second characteristics. We can also obtain the operation of plugging in fourth quadrant. In that case, this will be the characteristic curve. This is just a special case, which is not always used. Now I go to the third method, which is dynamic braking or induction motor. Dynamic braking of induction motor or rheostatic braking of induction motor. Here, we will see three different methods. One is AC dynamic braking, then with self-excited dynamic braking, third DC dynamic braking. Now let's talk about AC dynamic braking. When I say AC dynamic braking, I can have different connections. These are the three options that we have. This is the normal operation of motoring operation. A, B, C, three phases of the induction motors are connected to the three phases of the supply. Now, we can have two lead connection or three lead connection. When I take two lead connection, this B is connected, C is also connected, but A connection is disrupted. So this connection is not available. So this is two lead connection. When I say three lead connection, this is not connected, this A phase is not connected to the supply, but connected to the B phase. So this looks like single phasing. So this is exactly the case of single phasing. One phase is out. If it is just out, one phase is out, that we'll call it as two lead connection. If it is out and gets shorted with another phase, so AB is shorted, so we'll call that as three lead connections. So these are the two options that is possible. Now let's discuss about two lead connection. Now when I talk about two lead connection, because this A phase is not connected anywhere, so current IA is equal to 0, and current IB is equal to minus IC, because I have only two currents present here, IB, IC. I know that IA plus IB plus IC is equal to 0. Because IA is 0, so IB is equal to minus IC, or IC is equal to minus IB. So I can write, how do we calculate this positive and negative sequence component of the current? I can write IP, that is positive sequence component, which is 1/3 IA plus alpha IB plus alpha square IC. This we have already discussed. We are aware of this, where alpha is equal to e to the power j 120. That means cos 120 plus j sin 120. 1 at an angle of 120 degree. That is nothing but alpha. Positive sequence component, negative sequence component are calculated from here. As we know, because it is a single phasing, so it is extreme case of unbalanced supply. So in that case, we can write these currents in three different components. One positive sequence component, negative sequence component, and zero sequence component. And considering neutral not connected, we can say that zero sequence component is not present. So we are not considering the zero sequence component. So we'll consider only positive sequence component and negative sequence component. So this is the positive sequence component, 1/3 IA plus alpha IB plus alpha square IC. Now IA, we know in this case it is 0 and IC is minus IB. So substituting it here, alpha IB minus alpha square IB. So this gives alpha minus alpha square into IB. Now what is alpha minus alpha square? For alpha minus alpha square, one second. You can just see it here. For alpha minus alpha square, alpha is cos 120 plus j sin 120 minus alpha square, which is cos 240 alpha square, so it is 240. So minus cos 240 minus j sin 240. Now if I substitute the values, I get cos 120, which is minus 0.5, cos 240, which is again minus 0.5. So this two will get cancelled. This is plus 0.5 minus 0.5 will get cancelled. And sin 120 is root 3 by 2. Sin 240 is minus root 3 by 2. Substituting it here, we'll get it as j root 3. So alpha minus alpha square is j root 3. Substituting it here back, alpha minus alpha square is equal to j into root 3. So root 3 by 3, that gives me 1 by root 3. So I can get it from here, j ib by root 3. So this is the positive sequence component. And what is the negative sequence component? Negative sequence component is 1/3 ia plus alpha square ib plus alpha ic. Phase sequence is opposite. So this is alpha square. Here it is alpha square and this is alpha. Now from here again, by substituting, ia is 0, ib minus alpha ib. In place of ic, it is minus ib. So from here we get alpha square minus alpha. So this will be minus j ib by root 3. So this is the negative sequence component. So positive sequence component of current and negative sequence component of current has the exactly same value, but the direction is opposite. This is negative, this is positive. So this is IP and IN calculation. Now what is VP and VN? We can write this total voltage is VP minus VN. VP is in the positive sequence, VN is negative sequence. So overall voltage can be calculated as VP minus VN. So to obtain that, 1/3 VA plus alpha VB plus alpha square VC. So this part is VP, positive sequence component, and this is negative sequence component. Here alpha VB, here alpha square VB. So summing it up, we get 1/3 alpha minus alpha square into VV minus VC. Alpha minus alpha square is equal to j root 3, that we already know. So now substituting, we'll get j VBC by root 3. So total voltage, overall voltage, we apply it to this combination is this. Now when we get one positive sequence component and one negative sequence component, they are basically connected in series, right? So, but in the opposite direction, series opposition, we can say. Two equivalent circuits, one is for positive sequence component, the other one is for negative sequence component. They are connected in series opposition. And what is this summation of voltage? The final overall voltage, that is j VBC by root 3. Now let's draw the equivalent circuit. So this part, if you see, is the positive sequence component. In induction motor, what do we have? We have an RS. RS is stator resistance, stator reactance, and we have this part, rotor reactance with refer to stator and rotor resistance with refer to stator, which is RR dash by S, and this is XM. Okay, so this part we had drawn for equivalent circuit of induction motor. So we'll write exactly this part for positive sequence component, and also we'll write the same part again for the negative sequence component. This positive sequence components part and negative sequence component part are exactly same with only one difference. Here the positive sequence part, sleep is S, and for the negative sequence part, sleep is 2 minus S. For negative sequence, sleep is 2 minus S. That we have also seen this calculation in the previous case. For negative sequence component means the phase sequence is opposite. That means the voltage that we get, the generated rotating magnetic field that we get will rotate in the opposite direction. So speed is again, synchronous speed is again minus omega ms. So if we calculate slip, it will be 2 minus s. So for negative sequence component, we get, for negative sequence component, the sleep is 2 minus s. This is the only difference. Remaining things are same. So sleep is 2 minus s. So this is for the positive sequence component part, and this is for the negative sequence component part. So this is equivalent circuit. So now if I obtain the torque, speed torque characteristics, this is the positive sequence component speed torque characteristics, this is the negative sequence component. Adding these two, we get this for the net torque, the total torque. Now we can see that the torque magnitude is less in case of two lead connections. Net braking torque is small and therefore braking is not very effective. Now coming to three lead connection. For three lead connection, as we know, we have seen this diagram here. In three lead connections, what we have, A phase is connected to B. So here we cannot get a relationship between the currents. We can rather get a relationship between voltages. This A point is connected to B. So VAB is equal to 0. So I can write for three lead connections, VAB is equal to 0 and VBC is root 3V and VCA is minus root 3V, where V is the phase voltage and VBC is root 3 times of that and VCA is minus root 3 times V. Now what is positive sequence components line voltage? That's nothing but VAB plus alpha VBC plus alpha square VCA divided by 3. So one bracket is missing here. So 1/3 of VAB plus alpha VBC plus alpha square VCA. Now, when I substitute these values, VAB is 0, VBC is root 3V, VCA is minus root 3V. So again, I get alpha minus alpha square into root 3V by 3. So if I simplify, I'll get JV, because alpha minus alpha squared is equal to, that we have already seen, alpha minus alpha squared, which is equal to J root 3V. So we'll get J into root 3. So when we substitute here, we'll get this VP line is equal to JV. So this is the positive sequence components line voltage. Similarly, if I calculate line voltage for the negative sequence component, I'll get 1/3 into VAB plus alpha square VBC plus alpha VCA. So if I simplify, I'll get minus J into V. These are the line voltages of positive sequence and negative sequence values. Now when I take the phase voltages, so whatever value we are getting divided by root 3. So magnitude wise, VP and VN has the same value, V by root 3. Now again, in two lead connection, whatever diagram we have got, in three lead connection, we'll get the same diagram. Note one small thing in this notes, the diagram is missing here. Diagram, the equivalent circuit for the equivalent circuit for the three lead connection is missing. I'll just show you from here. This is the equivalent circuit, exactly same. Whatever we had, it's exactly same. Only the third line, this line is missing there. So we'll have a line here, three lines are there. This part is the positive sequence component, this part is the negative sequence component, and you have this third line through which the summation of this IP and IN flows. So this is IP plus IN. Okay, so this is IP plus IN, and speed torque characteristic remains same. Only thing is that torque will be slightly more here with respect to the two lead connection. So this is about three lead connection. Now coming to self-excited braking. using capacitors. So how do we get this self-excited braking? To obtain this self-excited braking, 3 capacitors are connected across the motor terminals. Now values of this capacitor is to be chosen such that when disconnected from the line, motor works as a self-excited induction generator. So motor has to operate as self-excited induction generator with these capacitors connected. Now this is the connection diagram. This is the connection diagram. You have the capacitors connected here. 3 capacitors connected between the lines. Now when I write the characteristics, this curve A shows the no load magnetization curve. This curve shows the no load magnetization curve. A curve, this curve. And this B curve shows the current through the capacitors. And current through the capacitors can be calculated by this equation. So voltage divided by XC. Voltage is √3 times phase voltage. So this is your current expression, and from this expression we can write that this V graph is the current graph. Now what is the operating point? The intersection point of these two. So the C point is the operating point. Now if this curve, when the speed is changed, when the speed is varied, then rather when I say the speed is reduced, then this magnetization curve will come towards this side, and this characteristics will go towards this side. So for a reduced speed, the small a and small b, these are the corresponding curve, and the C is the operating point. Now as the speed reduces further, we can have a point when this A graph and this B graph does not intersect at all. So when they do not intersect, then self-excited braking is not possible. Okay, so this is magnetization curve and this is current graph. The intersecting point is the operating point. When the speed reduces, this graph comes towards this side, towards small a, and this capital B graph goes towards this side as small b. The intersecting point, small c, is the operating point now. If the speed is further reduced, you can have a time when this A graph and B graph does not intersect at all. So we have a speed limit for which this self-excited braking is applicable. So below that certain speed, these two curves fail to intersect and the machine therefore does not self-excite and braking torque falls to 0. And this is the speed torque characteristics under this condition. Going to DC dynamic braking. Now when we talk about DC dynamic braking, we obtain dynamic braking but connected DC supply. Here also we can have a star connection or a delta connection. When I take star connection, this is star connection between A and B, the DC voltage is connected. C is not connected anywhere. So this is a 2-lead connection. For this, we have between A and B, DC supply is connected. C is connected to B. So it's a 3-lead connection. For this is delta connection. Between A and B, DC supply is connected and C is connected to B. So this is 3-lead connection again. Here, in between A and B, DC supply is connected. C is not connected anywhere. So this is 2-lead connection. So A and D are 2-lead connection. B and C are 3-lead connections. So by using this connections, we can obtain DC dynamic braking. Now let's take any one example out of these 4. All these 4 are possible. Let's take this connection. The first one. With that, this is the circuit diagram. So C terminal is not connected anywhere. You have this. This is open. C terminal which is open. From B and A, in between these two, through this isolation, we have a rectifier connected. So DC supply is connected between A and B. Now, when this DC current is applied, DC current flows through the stator. So it produces a stationary magnetic field. When AC is supplied, it will produce a rotating magnetic field. Here it is a DC current which is supplied, so it will produce a stationary magnetic field. Now, rotor and this stationary magnetic field, motion of rotor in this field induces voltage in the rotor winding, that we can understand. What will happen? There won't be any relative speed. So the machine works as a generator. Generated energy is dissipated in the rotor circuit resistance, and thus it gives the dynamic braking of induction motor. We know in general dynamic braking means the motor's energy is dissipated in the connected resistors. Okay. So when field is stationary, relative speed between rotor conductor and the field is now omega m. Field is not rotating. So relative speed between rotor conductor and the field is nothing but the rotor speed. So it is equal to omega m. Frequency of induced voltage will be equal to the frequency of AC source voltage if omega m is equal to omega ms. Now when I calculate sleep, sleep is equal to relative speed divided by synchronous speed. Relative speed is equal to omega m now. So relative speed is omega m divided by omega ms, and omega m can be written as 1 minus s into omega ms. Omega ms gets cancelled. So sleep in this condition is 1 minus s. So when I talk about DC dynamic braking, the sleep is 1 minus s. This is the equivalent circuit that we can get. These are the A and B. These are the rotor equivalent circuit, and these are the stator equivalent circuit. This is your complete equivalent circuit. So this is DC dynamic braking. So different types of braking we have seen in this class. Thank you.